Okay, so let's talk about the Earth's tilt, rotation, and the cause of the seasons, because this is going to give us a lot of information about how we can determine what the climate of the Earth is like in different locations, and therefore what kind of ecosystems we're going to find. So the Earth rotates at a speed of a little over 1,000 miles per hour. And since it takes about 24 hours to make a full rotation, that means that the Earth is about 25,000 miles around at the equator. So day and night are caused by the rotation of the Earth, where for about half of the day the Earth is facing the sun, and then the Earth is going to rotate away from that, bringing us to the dark side and causing night. At any one moment in time, half of the Earth is in darkness and half of the Earth is in daylight. So let's try a little thought activity here. But what would happen if the Earth didn't rotate? Well, if the Earth didn't rotate, then you'd have a very interesting situation. If the Earth didn't rotate, then basically the same side would be facing the sun at all times. However, as the Earth moved on around its revolution around the sun, for about 6 months, the surface would be facing the sun, and then it would move into a 6-month night. So temperatures would be extremely hot, probably well over 100 degrees at all times, and for about 6 months of the year, and then it would go into a cold, frosty night for the other 6 months. Basically, life would be impossible on the surface through normal photosynthesis. Another possibility is what we call synchronous rotation. This is what the moon does with the Earth. The moon rotates at the same speed that it orbits around the Earth, such that the same side of the moon is always facing the Earth. That's why whenever you look up, no matter when, you always see the same side. This would result in a continuous day on that side, as it would always be facing the sun, and the other side would always be in darkness, and so temperatures would be even more extreme. All planets and moons eventually will reach synchronous rotation due to gravitational drag, but the Earth is so large that it would take billions of years for it to happen. In fact, it would take longer than the life of the sun itself. The Earth, however, rotates rapidly, and so because of our rapid rotation, we have short days and short nights. This results in the energy of the sun being distributed evenly across the planet, making temperatures much more moderate and livable. Okay, so let's visualize what this would look like. In this example, what we're going to see is that, just imagine that where you see the Earth on this image is the sun, and that the moon is the Earth. So this is what it would look like if you didn't have any rotation at all. You'll see that the white side there is facing the sun for 6 months of the year. As it reaches the top there, it begins to get to dusk, and then now you've got 6 months of darkness. And so you'd have extremely long days, half the year, and extremely long nights, extremely high temperatures, and extremely cold ones, depending on which side is facing. This next one is showing what the Earth does in reality, which is a rapid rotation, where the days and the nights are really short, in our case 24 hours. And so because of this rapid rotation, you have an even distribution of energy across the planet, and therefore moderate temperatures that allow for life. Finally, this is showing what a synchronous rotation would look like, and in this case, that red side is always facing the Earth. And this, or if the Earth were the moon, basically you'd have one side blistering in the sun at all times, probably reaching temperatures that would melt the rocks, and the other side always in the darkness. In fact, Mercury does this around the sun, and the dark side is at temperatures that are so cold that ice remains in its craters because it never faces the sun, despite the other side of the planet of Mercury basically being 700 degrees Celsius. So basically you've got synchronous rotation would be actually the worst possible scenario for the Earth. Luckily, we're not going to see that for long after the life of the sun itself. And this is showing what the moon does as it goes through its synchronous rotation around the Earth relative to the amount of sunlight that's hitting it as it goes through the phases of the moon. Okay, so
Previously,
here's
I've
some
talked about
questions
how
for you.
quickly
What
the
would
Earth
happen
is rotating,
if?
and I've talked about why it's spinning. But what would happen if the Earth suddenly stopped rotating? Keep in mind, this is totally impossible. Still, I find topics like this super interesting to think about. If the Earth actually stopped rotating instantly, it would be very, very bad for everything on the surface of the planet. Consider this. If you're standing on the equator, you're traveling at 465 meters per second from west to east. If the Earth put on the brakes, your momentum would keep you flying at the same speed until friction slowed you down. Imagine the jumbled forests, oceans, buildings, and unfortunate animals after that event. It would be carnage. The atmosphere is also turning at 465 meters per second with us. If everything suddenly stopped, it would be like a simultaneous hurricane of epic proportions on almost every part of the planet. The closer you get to the poles, however, the less damage it would cause. If you were standing on the North Pole, you'd hardly feel it. Let's imagine the Earth slowed down more gradually, taking a few days to come to a halt that didn't tear the landscape into a fine mist of dirt, seawater, and a variety of organic material. The stars would hang fixed in the sky. Only the planets would move around, continuing their paths around the sun. A day on Earth would now last 365 days. In other words, it would take a full year for Earth to fully orbit the sun, bring it back to the same location in the sky. Each year would include one long day and then one long night. You can imagine how that would be devastating to plants and animals. You get a hint of this at the poles, where you can experience weeks of permanent night and weeks of permanent day. But imagine 6 months of night followed by 6 months of day. The planet's tilt gives us our seasons. As we define the Earth's tilt as its rotation in relation to the sun, a stationary planet would effectively have no tilt at all. Without that tilt, there'd be no axis and no seasons, although we would still have north and south poles. Because of its rotation, turning once every day, the Earth is actually a flattened ball, or if you prefer, an oblate spheroid. Without that rotation, the Earth would become a perfect sphere. This sounds interesting and probably harmless, but it's actually a big problem. Because of the Earth's bulge in the middle, the oceans are held out at the equator by 8 kilometers. On a perfect sphere Earth, the world's oceans would redistribute, flooding many of the regions of the planet with an immense volume of water. We'd end up with a single continent around the middle of the planet, with oceans surrounding the north and south poles. Let's assume that if the Earth stopped turning, the Earth's core would stop rotating with it as well. This natural dynamo generates the magnetic field that surrounds our planet and protects life from radiation from space. Whatever life still alive would be irradiated from the sun and cosmic rays if it didn't live underground. So if the Earth suddenly stopped turning, it would be very bad, even catastrophically bad. Fortunately, it's completely impossible for this to happen.
Thanks for watching. Now make sure you click subscribe on our YouTube channel over here. And maybe you've still got some questions about space and astronomy, like this one or that one. And if you don't see the question you're looking for, then send me an email at info@universetoday.com.
Are you just punching me in the shoulder?
No.
Just protect me.
Okay, so the Earth's axis and tilt represent how the Earth spins relative to its plane with the sun. So the Earth is tilted at 23.5 degrees, and what this means is that during certain times of the year, the Earth is facing toward the sun in the northern hemisphere, and the northern latitudes at the Arctic Circle get 24 hours a day and no night. However, as it rotates around to the winter time, now you've got 24 hours of darkness. This tilt thus results in a big impact on the distribution of energy that's hitting the Earth's surface. The further north you go, the more extreme the difference between winter and summer. The tilt has no effect at the equator, thus the equator has basically the same weather year-round with warm temperatures and days that are both 12 hours a day and 12 hours a night all year long. The further north you go, the more extreme these become. So you've got these long days of summer followed by these long cold nights of winter. And therefore, you have these differences in temperature that can be quite dramatic. And the further north you go, the more extreme these differences become. If the Earth were not tilted, there would be no seasons because the entire planet would receive the same amount of sunlight evenly distributed 12 hours a day and 12 hours a night throughout the year. Now the North Pole and the South Pole would still be cooler than the equator, but there'd be less of a difference in those temperatures due to the fact that they're getting that same amount of sunlight throughout the year. As we look at this image here of what does the winter solstice do, it has dramatic impacts on the slope or the angle at which the sun is hitting. So you can see here in this scenario at 48 degrees north, or about the latitude of Washington state, you'll see that on the shortest day of the year, on December 21st, the sun rises in the southeast, barely hovers above the horizon, and then sets in the southwest. This low angle of the sun facing the south at all times results in long shadows forming to the north. So if you're a mountain that's oriented such that you've got north and south aspects, these long shadows result on the north side of the mountain basically getting no sun at all throughout the winter. As you move to the spring equinox, this is the time in which every part of the planet receives exactly the same amount of light, 12 hours a day and 12 hours a night equally. The sun rises due east, still sort of has a southern angle to it because you're up to the north of the equator, and then it sets in the due west. Notice that the shadow facing the north is basically shorter. As we move to the summer solstice now, the Earth is now angled toward the sun in the northern hemisphere, and you've got these long days where the sun rises in the northeast, goes high above overhead, resulting in virtually no shadow at noon, and then sets to the northeast. And now, instead of a very short day, perhaps only 8 hours of sunlight in the winter, you're at 16 hours of sun in the summer. And the further north you go, the more extreme this becomes, such that when you go above the Arctic Circle, the sun basically doesn't set. It just kind of does a circle in the sky throughout the day. As you move to autumn, the sun will begin rotating back down toward the south, and those shadows get longer. What the impacts of this looks like on an ecosystem. So this is a picture of the Olympic Mountains in Washington State. We've got a range of mountains that are oriented from the west to the east. So on the winter solstice, the shortest day of the year, the sun stays low in the sky, barely hovering above the mountaintops. And as you see on this line, that's the line that has the shadow. That valley that you see below that yellow line will be in perpetual darkness throughout the entire day. In fact, the bottom of the valley will not see sun actually hit the ground for several months of the year. This means that it's colder, snow is going to last on the ground longer, and it's going to have an impact on the ecosystems that live there. As you move toward the spring solstice in March, the angle now of the shadow is much more pointed downward. You'll notice that there's a lot more snow up there. All these north-facing slopes have accumulated snow throughout the winter, with March being the season where there's the most snow, as it's built up through the winter. But now, for the first time in weeks, the sun is starting to hit the bottom of that valley. As we move to the summer solstice, you'll see that there is no shadows at all. The sun is high in the sky, and even the north-facing slopes are starting to get a lot of sun. The snow's melting back, but the snow is going to linger long into the summer, especially on those north slopes, because of how much built up and didn't melt out in the shadows of the winter. As we move toward the autumn solstice, the shadows begin to stretch back out across the valley, and for the next several weeks or months, that valley bottom will never see sunlight again. So here's a question for you. June 21st is the summer solstice. It's the longest day of the year in the northern hemisphere. Yet if you look at temperatures, you'll see that the temperature is actually hotter in July and August on average than it is in June. Why is that? Also, as you look at December 21st, the shortest day of the year in the northern hemisphere, you'll notice that the temperatures in January and even February are actually colder than they are in December. So why is it that the longest day of the year isn't the hottest time of the year in most of the northern hemisphere? It's later in the summer. And December 21st is the shortest day, yet the coldest temperatures often happen in the month or two after that. Well, it has to do with basically what we call heating momentum. So what happens as you move through the summer is the sun has been hitting the ground in the long days of summer for weeks and weeks and weeks. And so as you move into July and August, it's had 3 months of heating versus in June where you've maybe only had 1 or 2 months of heating. As you move into August, even September, it's been heating for much of that summer, and so you maintain these warmer temperatures. As you look at the spring equinox in March and the autumn equinox in September, you'll notice that September is much warmer than March. That's because as you move into the winter, it's been cold for a long time, and so the ground hasn't, and the water of the oceans have not been able to absorb much solar radiation in those short days of winter. So we have always a shift in the season of what's the hottest time and the coldest time, a little bit off on the order of a couple, 3 weeks from the actual longest and shortest days. Okay, so thought questions 1 and 2. What would happen if the Earth did not rotate? And if the Earth were not tilted? So, if the Earth did not rotate, would there be days and nights? The answer is yes, but a day would last for 6 months and a night would last for 6 months. And if the Earth's axis were not tilted, there would be no seasons, because even though the equator would be hotter and get more sunlight than the poles, those specific locations would get the same amount of sunlight throughout the entire year, 12 hours of sun and 12 hours of darkness. All right, one more thing to think about. What if the Earth were tilted 90 degrees on its axis? It was totally on its side. What would that look like?